Good. Welcome, everyone, to App 306 Integration Patterns for Distributed Systems. My name is Maximilian Schellhorn. I'm a Senior Solutions Architect working with AWS, and I'm mostly focusing on serverless, SaaS, Java, and event-driven architectures. And today I'm joined by Dirk.
Hello, everyone. I'm Dirk, Principal Solutions Architect with Amazon Web Services. I enjoy being an Amazonian for 8 years and 8 months now. I also work with software companies, working with them on their multi-dimensional transformation, which includes product and technology strategy, organizational transformation, and of course, software architecture guidance on topics like the ones we discussed today.
Yeah, and Dirk and I, we have both been working on distributed systems over the last couple of years, and we think it's safe to say that modern systems do not live in isolation. So modern systems, they communicate with each other. They communicate internally, they communicate externally to third-party APIs, and we even see new forms of integration evolving, such as agent-to-agent communication and new protocols such as MCP, the Model Context Protocol.
In a nutshell, we think if we build a system A, then there's a high likelihood that we also want or need to integrate it with system B. And at first glance, it looks quite simple, doesn't it, Max?
Yeah, it's just 2 boxes and a line between them. But actually, is A sending something to B, or is B pulling from A?
Great questions. From a design perspective, you actually want to know where data flows from which end to what end. And so is A sending conceptually data to B, or is it the other way around, or are actually both communicating with each other? That's all the questions that you want to know. But now, if you have concluded on that, there are a ton of design decisions that you need to take into account. And all of them come with their specific benefits and trade-offs. So I guess that's also a good moment to throw in my favorite law, which you can see here, and I also like to call the beware of the faith healer principle. And that is maybe one of the main takeaways also from today, that every design decision that you take, it always comes with a trade-off. And actually, we don't want it. With our mental laziness, we want to have it all without any adverse effect, but that's actually not the case in reality. Or in short, there's always something that sucks, whatever we do and decide. So, and as we have seen before already, there are plenty of design decisions, and even a 45 minutes dedicated talk on this would not be enough. So we had to make a selection of a few aspects of distributed systems, and we're going to look at those from the integration patterns perspective today. The first one is coupling and its dimensions, and that's all about dependencies between systems. And we will also see that coupling has many faces. The next one would be control flow and flow control, when we want to understand nuances between push and polling data and how to manage complex interactions between systems. And last, we'll check on delivery semantics and message order, and we look at some ubiquitous questions why things become complicated when you have concurrency or something goes wrong. And with that, let's jump into the first pillar.
Yeah, thank you, Dirk. So let's start off with coupling. And why care about coupling? I mean, Dirk, I don't know about you, but I need stability in life.
Absolutely, same here.
Yes, and I also need stability when building software. So I was looking for some guidance, and luckily I found Mr. Larry Constantine saying a structure is stable if cohesion is high and coupling is low. So we have 2 things, cohesion and coupling. And cohesion is the degree to which a module's internal belong to each other. So it's about identifying proper service boundary. So things like domain-driven design that care about that. So if I have an order service, I want to make sure that everything that goes into the order is within that dedicated service. Now, the second point is coupling. And coupling is the degree to which a module depends on another module. Because after all, we want to create a meaningful whole system, so therefore we have multiple components. And we want to emphasize that coupling is not a binary state. So it's not just coupled or uncoupled. There are many different dimensions, as we will learn the way. And we will also learn that essentially the process of decoupling might introduce other forms of coupling at other dimensions or introduce additional complexity. And to showcase this, we want to focus today on mainly 4 different dimensions. So location coupling, so does service A need to know where service B is? Then format coupling, does service A needs to know how to communicate with service B? Is it JSON RPC, gRPC, REST API, some binary protocol? And then temporal coupling. So do I have a timing dependency on the other service, both from an availability perspective, but also from a processing time perspective? And last but not least, we have domain coupling. And this is usually some form of coupling that we always accept because we need to know some form of understanding of the other system's domain when we're connecting systems. Now, we wanted to avoid having a philosophical discussion today. So before we dive into the sample application, I would like to invite you today to spend some of our coupling budget together. So we will use the concept of a coupling budget to compare different architectures with each other and see what effects our architectural decisions will have. It's important to note that this is not an absolute measure. So Dirk, it's not about you have now 3 coupling points that you can spend.
Oh, that's bad.
Yeah, unfortunately. But it is rather a concept. It's about being mindful where we accept, reduce, or reject coupling. So to give you a simple example, let's do synchronous communication with APIs. You probably all know that, synchronous HTTP between 2 systems. And if we now show our coupling budget in that picture, we see that we are location, format, temporal, and domain coupled between the 2 systems. So location coupled because A needs to know where service B is, be that be a DNS name or an IP address or something like that. It is format coupling because B essentially dictates if it's a REST API or something like that. We are temporal coupling in the sense that if B is down, A cannot fulfill its functionality. And also A is relying on or has to wait on the processing time of B to finish its functionality. And last but not least, if this is order service calling invoice service needs to understand something about the invoice services domain, like the payload and the semantics of that. And this might be totally fine if you have 2 applications or in very simplified scenarios, but it will get a bit more complicated when we're introducing a more sophisticated example.
Right, to make it more tangible, let's have a look at a real-world example in the context of a ride-share application. So I guess I don't have to explain the overall context. Everybody knows what ride-share is. And this particular use case is about pre-booking rides for instance, next week, already this week. And that might also come with some marketing campaigns that put some pressure on our back-end systems. So how does it look like? Most certainly, the end customer has a mobile app. They type in all the details for the ride, send it to the back-end, which is the ride booking service, and eventually get back their response that the booking has been processed. But hey, of course, we have a modern backend under the hood with a number of microservices and downstream systems. And since we are currently integrating synchronously with APIs, we can also have a look at all the time that is spent in the specific downstream systems for processing those requests and the parts of those requests. And due to the fact that we have synchronous request paths, all that processing time adds up. And it takes quite a while, actually, until the response comes back to the customer, which is, in the end, a quite lousy experience. And it can be even more lousy when there's high pressure on the system, and you also need to help yourself with mitigation patterns like circuit breaker. So this is why I also like to call such an architecture lousy coupling, in contrast to loose coupling. And I guess Roy Fielding would actually call it out that it should be X-rated because there's so much coupling on screen here.
Good. So let's see what effects that has on our coupling budget. So now if we introduce all the points, we see that we're being quite hard to our overall coupling budget because we not only have the coupling now on the first layers, but we are also introducing that on the downstream services of our downstream services, essentially, right? So overall, that has quite a heavy effect. So Dirk, do you have an idea what we could do to simplify that or make it less coupled?
That's super obvious. We should all throw it away and let Gen AI create a new application from scratch. How does that sound?
A very perfect suggestion, but maybe we start with a less invasive approach.
Okay.
So we start first of all with doing an asynchronous API. So instead of throwing everything away, we just change our APIs. And instead of waiting for the processing time, the downstream service just returns back a 202 accepted. So in that case, now you see that on the animation, we are essentially reducing the temporal coupling, but we're not completely removing it. Why is that? Because we are still availability coupled on the other service. So if the service is down, it doesn't help me that its processing is asynchronous, right? But because it's down, I cannot even talk to it. Now, Dirk, can we maybe do something to simplify that a bit better?
Yes. I guess we should look at the availability dependency here to also come to a better user experience. And this is the moment in time when we should introduce message queues, because message queues decouple both sides, A and B in this example, from each other. So the systems only talk to the queue now and not with each other anymore. And message queues have the very nice characteristic that they buffer messages, and that means they reduce the availability dependency to an absolute minimum. And it also helps downstream systems to flatten peak loads. If we employ queues now in our sample architecture, we would see between pairs of systems, upstream, downstream, we would see a queue. And to not overload this diagram too much, we only have put the downstream path, so the request path into it and not the response path. Of course, this has to happen as well. And let's simplify the diagram even a little bit more to also have a look at what could actually bring us a nice implementation for those queues. So you might notice that if we employ messaging here with queues now, we shift the operational responsibility for that integration to the messaging system, which is great, yes, for us. But then you also need to make sure that you have a really reliable, scalable, and available messaging system. And this is why we would typically propose and suggest that you use a managed serverless service like Amazon SQS for that. But if you're bound to industry standard protocols like JMS, for instance, you can only make use, you can also make use of Amazon MQ, which brings you a managed Apache ActiveMQ or RabbitMQ.
Good. So let's look into what effect this architectural change now has on our overall coupling budget. And you see now things shifted a little bit. So first of all, the most obvious one is we're no longer location, format, and temporal coupled on the actual downstream services, but we need to keep in mind that we're now coupled in that sense on the actual messaging system. Right, so if we go back to the before and after state, so you see this was before, we were basically coupled on every different service that we integrate with, while now we are shifting that to the messaging system, right? We are still location coupled in a sense because we need to know obviously where the messaging system is, be that be the regional SQS endpoint or your Kafka broker. We are format coupled in a sense, but in a better way than before, because we're now standardizing all our producers and consumers to talk that specific protocol, right? So we're using the Kafka SDKs, for example, or the SQS SDKs. So both the producers and consumers basically agreed now on a unified format, but still it's some form of coupled now that you're introducing. And last but not least, you're not temporal coupled anymore to the downstream services, but you still need to keep in mind that your messaging system essentially becomes a single point of failure. And this is why it's very important, as Dirk mentioned, to really make sure that this is highly reliable, that you have a multi-broker setup or a serverless service, that you're really reducing that reliability on that aspect. But you might have noticed here on the left side, you still have all the domain coupling points. So why is that? Because essentially, we are still telling the other systems what to do, but in a more decoupled way. But we're still sending commands, right? So we're sending find a ride, do a payment, add loyalty points. So the ride booking service still has a domain understanding of all the different downstream services. And while that might be okay for a smaller architecture, we see if we are evolving that and we're adding multiple downstream services, we are getting quite heavy now on overall coupling budget. And we're also violating cohesion in a sense, because whenever something changes on the downstream system, we still have to change the right booking service, which violates our cohesion aspect. So Dirk, can we do something about that?
We want to help the right booking service to get rid of those domain coupling points, don't we?
Let's help them.
Right, awesome. So we can introduce another asynchronous integration pattern that's a different type of channel than the queue, which is a publish-subscribe channel, or in short, pub-sub. In contrast to point-to-point channels like queues, in a pub-sub channel, every system on the right-hand side receives every message. We call them subscribers in this case. And if we convert this to our sample architecture, we can now make it a lot simpler for the right booking service to address all the downstream systems, because it can just send one message to the pub-sub channel, and all the systems on the right-hand side will receive that channel. And it allows us even for another transformation, because I know we all love the request-response pattern. We are used to it for maybe decades or so and have used it. But actually, this now gives you the opportunity to transform into more of an event-driven concept and architecture. Because now there is one other difference here. The right booking service doesn't have to know what the downstream systems want to see. The downstream systems need to understand what the right booking service sends them. So the right booking service can now just send an event. A ride has been booked with the necessary details, and the downstream systems need to make sure they understand. And again, you're pushing the operational responsibility to the messaging system, and I would again recommend look at serverless managed services first, like Amazon SNS or Amazon EventBridge. And if you're bound to Apache Kafka, I would recommend to use Amazon MSK for this.
Good. So let's take a look again into our coupling budget and what does it mean. So first of all, we're still having here a messaging system, that because it's our pub-sub system. So from a location format and temporal aspect, nothing really changed in compared to the queues. But you might have realized that the actual domain coupling now shifted from the left side to the right side. And why is that? Because it's the right bookings domain having the right book event. So in that case, it doesn't need to know what happens downwards. So if we see that before and after, we see if you count each individual dimension, overall you would have the same amount of points, but relative to each individual service, you only have a single coupling point from a domain perspective. Because now it's the decision of the consumers to couple themselves to the right booked event. And you might ask yourself, okay, in which case do I do which of those two options? And the essential questions that you need to ask yourself is, on which side do you want to couple? So there's no right or wrong. But the question you ask is, on which side? And the first one is, if you decide to couple on the producer side, you usually do this when you're doing commands and you expect a response and you need something to happen. So the producer needs something to happen. So if I'm an order service and I can only fulfill my functionality after the payment has finished, this is an instructed command, essentially can be synchronous or via request response with a queue implementation, but the decision is on the producer side. And the other side is the decision to couple is on the consumer side. And we do that when the producer does not care about if something happens at all with it. So it just says, I booked the ride, I don't care what happens, if you're adding loyalty points and what not. So the decision to couple is on the consumer side. And you can actually see that now in our ride booking service, we can have two things. So we can first of all do it for the payment service. We decide to couple here on the producer side. And sometimes you even don't have another choice because you're talking to an external system. They don't provide an async or an event-based API. So therefore, you only have the choice to integrate like that. But then, on the other hand, we can still publish an event and then let whoever wants to subscribe to it to that event. Dirk, you look like you have a question.
I do have a question. So we now got rid of the nice characteristics of queues that took away the availability dependency of the downstream systems from us. Why did we do that?
Yeah, actually, we can still introduce our queuing behavior, and we will learn a bit more about that in the push versus pull example. But a pattern that we often see is with SNS and SQS, you can still, on the fan out, on the pub sub, you can still add queues in between. So you have a topic queue chaining essentially to keep the best of both worlds if you want to do like batching or things like that. So we conclude that with saying that coupling is never absolute, but relative, right? So you have, even if you count all the different dimensions you have seen, it's relative to each individual service on how we are going to couple that.
I guess we could continue the discussion about coupling for several hours, but we also need to continue with the next chapter, which is control flow and flow control. No pun intended here. Both things are fundamental aspects of distributed systems design. And let's start with push versus pull. We have mentioned it already for a few times. And if we look into this, we see on the top of this diagram the data flow. In previous architecture discussions, and basically in most architecture discussions, the data flow is actually examined. So everything is about the data flow, but there's also the control flow. And the control flow can also be in the opposite direction. We see it at the bottom here. In the case of pull, the downstream system initiates the data transfer. So the control flow is in the different direction. So actually, Max, I think that requires that we dive deep a little bit into it.
Let's dive deep into it.
Thank you.
Let's dive into push versus pull. And I want to start with push-based systems. So you see here a very simple example. So you have essentially event bridge where you can receive an event, and then you have rules that are triggered on a certain payload content, and then the message is pushed to a downstream service or system. Now, the benefit of it is that the sender owns the integration logic. So usually you see that when you configure webhooks, right? So the sender basically gets the event and then pushes the event to the downstream service. So, and that enables now the sender to do a couple of things. It can do routing and filtering. So instead of sending everything or the consumer receiving everything, the producer can pre-filter and only send the relevant message to the downstream system. And that highly simplifies the consumer integration. And also the consumer does not need to manage polling intervals and so on and so forth. Now, in Event Bridge, for example, you have then the capability to do rate limiting. So if your downstream system cannot handle the load that you are sending, there are some mechanisms such as dead letter queues or rate limiting that the actual sender can back off here a little bit. And last but not least, as I already mentioned, it reduces the idle or wasted compute cycle, right? Because there's not a polling fleet saying, do you have new messages? Do you have new messages? It's really about just sending the messages when it actually arrives, which enables us to have real-time notifications. Now, on the pull side, however, the consumer owns the integration logic and rate. And that can be quite beneficial in a sense that we are basically able to have something like replayability between messages. It enables us to do queuing. So if I get a sudden spike of messages, the consumer owns the rate at which it consumes the actual messages. So it can flatten out peak logs. And then we have simplified networking requirements. And this is something that is often underestimated, right? Because in the push-based example, basically all the consumers need to be reachable. They need to be addressable in the network or being public. While on the consumer side, we're actually basically turning that around. So the consumers only need to have access to the actual messaging system, and that can simplify your networking requirements. And last but not least, since the consumer owns the integration logic, we can basically also act on a series of messages. So we can do windowing and we can do aggregation, which unlocks streaming analytics. So we can look at a large chunk of messages over a certain amount of time, then analyze that, and then maybe publish a discrete event afterwards. So it's really about push versus pull, and it both has its pros and cons. And you sometimes want to choose both. Again, if we go back to our example, we might have here an SQS queue between the ride booking service and the payment service. But then we have pops up with Event Bridge where we decide based on the payload, for example, if the order is above 100 euros or something, then we only notify the loyalty point system. So Dirk, are there any other aspects we wanted to look at?
I think there are. So let's also look now at choreography versus orchestration. And this is all about how we can manage the flow of interaction between systems. And for both patterns, we actually assume that there is a piece of work that flows through our systems and that we actually want to describe a workflow. Now, for choreography, this workflow is implicitly encoded pairwise into the processing steps that we now want to manage. And in orchestration, it's the other way around. We externalize that workflow and let an orchestrator component run it for us. So we see something like an event broker in the choreography part in the middle. And a typical tool to implement that event broker would be Amazon Event Bridge, again, a managed serverless service. And for orchestration, the recommendation would be to use AWS step functions for it, also a managed serverless service. So how does it look like for choreography? So we use Amazon Event Bridge in this case to send messages to it, and the next processing step will know that such a message is interesting and relevant for it, and then it goes through the entire workflow. So it's quite easy to get started with. And since we use asynchronous integration here, it comes with all the benefits of loose coupling. You can let autonomous teams work on the different systems that are involved here. And by the way, it's also a nice starting point if you want to transform your monolithic application into a landscape of microservices. If we put this into our sample architecture, we have this, now Amazon Event Bridge in the middle, and then we start sending events, and we send events, and we send events, and somebody thinks of new events, and there's no governance whatsoever, and after a while, nobody knows what events are wandering around. We end up with that big ball of mud. So it might not be as simple as it looks at the first glance. We have a few challenges with choreography that are manageable, but they need to be managed. And one aspect is actually the key characteristics of choreography, that this workflow that we are assuming is not externalized, but internalized in parts. And other than that, you also, if you need some transactional behavior or similar things, you need to implement this on your own. So this is additional heavy lifting that you might be able to do, but maybe also not. So some challenges that we have seen with choreography, maybe orchestration can help us to reduce those challenges. So what benefits do we get from orchestration? So first of all, if we use AWS step functions, it's very nice that we have a visual development experience because we can draw that workflow in the AWS management console. And then the key characteristics of orchestration come into place here, that we have the workflow externalized. So you can look at it at all times. You really know what's going on here. And it also brings you the functionality for transactions and rollbacks and so on. So you don't have to manage this on your own. Another nice thing with AWS step functions is that it comes with an integration with AWS X-Ray for observability. Let's have a look at the benefits of both approaches at once. And as usual, we wouldn't say you have to decide to only use this or to only use that. It's quite the opposite. You should always use the one that makes most sense in any situation. And in one single use case architecture, you can perfectly use both. So here we apply orchestration for these integration parts where we anticipate that we maybe need to roll back something and that might become complicated if we implement this on our own. And for the more simpler parts, we just go with choreography. So the best of both worlds within one architecture. Also, choreography versus orchestration is a talk on its own, actually. So we could spend hours on this, but we have one chapter left for today, which is delivery semantics and message order. And this is even more an area of heated discussion, as you have experienced yourself, Max. And I will say this is mostly, again, because of our mental laziness. We want to have it all, and we don't want to think about the cost and the trade-off and the practical implications when we say we must have exactly once processing period.
Let's see if I can give it to you, Dirk. So let's talk about message delivery semantics first. So message delivery semantics is, so a message is delivered 0 or 1 times, then it means it's at most once. So there might be some message loss into it. And at least once means that I get the message 1 or multiple times, so their message duplicates. But in a lot of conversation, people want something else. They want
exactly once.
Yeah, and only exactly once. They say, Max, if we're building a message-driven system, if I don't have exactly once delivery, I cannot build it. So let's see if that is actually possible. So what happens if we look at it from a producer side? So what does it take from the producer to have a message exactly once and then see if it's actually possible? So 2 things usually happen. So I add the message to the messaging system, and the first thing I need to do, or the messaging system needs to do, is store that reliably. So what does reliably mean? In case of Kafka, for example, I need to store it on multiple brokers, because if there's a broker outage, I might have a message loss if I only store it on a single broker. And the second thing that needs to happen is that the message needs to be acknowledged so that the producer knows, okay, it was stored reliably. So what is at most once in that case? So we have at most once if we are, for example, not storing the messages in a fault-tolerant way. So this is, for example, in Kafka, replication factor 1. I only have it on a single broker. Or if I don't wait for the message acknowledgement. So that can be, so we try to store the message reliably, but I don't wait for the response. So this is usually fire and forget. So in that case, producer does not know if the message was received or replicated properly. And this is where we get at most once. Now, if we look into at least once, it looks different. So let's say both things work well. So the messages are acknowledged, and we are actually storing the messages fault tolerant. So the producer knows that the message was received and replicated properly. But there can still be a network timeout. So let's say we are storing the message reliably, but then we are failing to acknowledge the message. So the producer does not know if the message is there or not. So in that case, the producer would retry sending that message. So we see that here. So we say messages might be delivered more than once to do producer retries. And this is a fact. So there is not such a thing as exactly once delivery, unfortunately. Dirk, I'm very sorry.
Yes, me too.
But we can have something that feels like exactly once delivery,
Yay.
but this is called exactly once semantics. And this is done by the messaging system having some form of knowledge, say, did I receive message A already? And this can be done via a deduplication ID, and it requires state. So deduplication ID in a sense that I need to compare 2 messages somehow to know that they are identical. And second, I need to have the state of the previously received messages. And the other thing is state is expensive usually and limited. So I don't have an indefinite state. So usually this deduplication logic is limited by either scope or time. So you see that in examples, for example, in Kafka, you have the producer, it's based on producer ID and a sequence number, but if the producer ID changes, you basically don't have this guarantee. And the second one is Amazon SQS, where you have a deduplication ID and a window, but this is limited to 5 minutes. So we conclude that the deduplication of messages in distributed system is always relative to a defined scope, and we cannot have exactly once delivery, at least from the producer side, but something that feels like that. Now let's imagine this is enough. So the scope is enough, and we only receive the message now 1 time in the actual messaging system. So can something happen now on the consumer side as well? So first of all, at most once from the consumer side can also happen. And I say, let's say I just acknowledge the message before I actually fulfill my downstream functionality. So in that case, if I break, I cannot re-get the message from the messaging system. So therefore, the message is delivered at most once. So I might have message loss. And this is good in scenarios where you value performance and throughput that are basically prioritized over the completeness. Now, at least once, again, let's say everything works well and we acknowledge the message. Again, similar to the producer, what can happen is that the consumer crashed during the commit. And then, for example, in SQS, based on a message visibility timeout, the consumer will get the message again and therefore receive it more than once. So again, messages might be delivered more than once due to a missing acknowledgement. So even though we fixed everything on the producer side, this can still happen on the consumer side. So also there, we cannot have exactly once delivery.
Good insight.
So how would exactly one semantic look like? You probably all heard about that, but you can have something like idempotent consumers or targets. So that means that if I reprocess the same message, that my action does not have a side effect. So if I do an insert and I then get the message again, I would probably check first if the message is already there. And you can combine that with optional with something like a processing store, where you basically keep track of all the messages that you have just consumed. And examples of that are exactly one semantic within Apache Kafka and its connector frameworks, or distributed transactions like a two-phase commit. So unfortunately, we cannot have exactly once delivery, but something that feels like it. I hope
that should be good enough.
Good. So let's see if we have something else on the order side.
Yes. So order, order, order. Again, we tend to say we require strict message order, but we don't always think completely through what that means in practice, because there are, again, costs and trade-offs that we need to pay for it. So let's have a look at message order. I actually liked, Max, that you looked at your topic before also from the producer's perspective, because in most technical content, only the consumer side is considered. And I think it's also super interesting to also look at the producer side. I will do the same here now for message order. And let's start with the very simple way. And it's similar to what Max has described before. We have one producer, and the producer sends messages, they get acknowledged, and we are good. So why is it the simple way? Because we only have one producer. Everything is simple without concurrency. But you pay for it with less throughput, with higher latency, but sometimes you cannot get around it if you work with legacy systems, for instance. So let's make it a little bit harder and introduce concurrency. Now we have two producers that send messages into the messaging system, right? We might have multi-threads, or we might have multiple customers who send messages in parallel. And it can happen that we have some glitch on the network connectivity between the first producer and the messaging system, so that it takes a while until the message comes in. And although message A in this example has been sent before message B arrives in the messaging system before. So is that a problem? Maybe, maybe not. Let's see. So we should definitely talk about total versus partial order now. It only is a problem if we require total order. But then we have also seen, or we can anticipate already, if you want to have total order, you can only operate in one single thread. So, but we will pick this up again in a minute. Another thing that we also should be aware of is the happens before relation. And we will see in the next slides how that could look like. And let's come back to our rideshare service with the example that we book a ride. And let's assume those two producers here are two different customers that make use of the service. Now, the first customer requests a ride, and the second customer also requests a ride. But after this, and again, we see the network glitch between the first customer and the messaging system, so that it takes a while until the message arrives in the messaging system. So again, message B, although it was sent afterwards, arrives earlier. And then also, maybe the first customer cancels their ride. And we want to make sure that we have a good understanding of the happens before relation here and are able to actually determine it. In any case, we want to make sure that A1, in this case, arrives in the messaging system before A2. And we talked about total versus partial order before. And here, in this case, we can clearly say we only rely on partial order here because we can process the messages for each customer independently, right? So we don't care that message B arrives before message A. What we do care is that message A1 arrives before message A2. And to make sure that this happens, it requires some coordination on the producer side. And with our rideshare app, it can be as simple as that there is no cancel button available until the ride book request has been acknowledged from the backend system. So that might be super simple, but it might also be impossible, and we still end up with the third case over there that we actually don't want to have, and then we need to manage this on the consumer side. Other than that, whatever kind of messaging system you are using here, you should also look at some of those constraints. That might be the maximum of in-flight messages. And in any case, there is something you need to do on the producer side to cater for the sharding that comes in with the partial order. So in case of Amazon SQS FIFO queues, you would add a message group ID to each message, and that determines which group it belongs to, in this case, which rideshare customer. And that brings us to the next insight, that order of messages in distributed systems is relative to a defined scope. Now, we also need to look at the consumer side. And I'm not spending time now to look at the usual way how you can apply SQS FIFO queues to make sure you have your partial order. I want to look at that one exceptional case that we couldn't solve on the producer side, that this A2 message arrives before A1 in the messaging system. So what can we do in this case? The typical way you approach this is that you have a helper table, and Amazon DynamoDB would really be a super useful tool for that. Again, serverless and managed system. So what you do here is you store the incoming messages and also store what the current status is. So in this case, we receive message A2 first, and we put it in our table and also put a pointer there, so to speak, that this is the latest one that we have received. Now we receive message A1, and it is quite important that we know the happens before relation. How can we interpret it based on business data, hopefully? And for the second, and we even have a duplication of A1 in this case, and here it comes into action again what Max mentioned before. Idempotent consumption is always super recommended, so you should always take care of that. And I would also say make a business identifier the base for your idempotent discussion and not a technical identifier. So you can just throw it away, or you do an upsert in your table in this case. So, but how do we make sure that we actually know about that happens before relation? So how can we re-establish the right order in our helper table here? So for that, we need something like a monotonic clock. And that doesn't necessarily have to be a clock in terms of timestamps. It can also be a well-defined sequence of statuses, right? And in this case, we know that the status requested will always happen before the status cancelled. All right, and with that, we conclude also on this chapter and have one last look at the three fundamental aspects of distributed systems that we looked at today. So we started with coupling and its dimensions, and we learned that coupling decisions come with a cost, as every other architecture decision. We looked then at control flow and flow control, and we learned that it's always a good idea to use a healthy mix of patterns for trade-off optimizations, and that applies also everywhere. And then lastly, we looked at delivery semantics and message order. And here we learned that everything relates to a scope. So before we say thank you and goodbye, Max has another totally unrelated announcement to make to you.
Yeah, I don't know how that came into there. So if you haven't heard about that, the EU Sovereign Cloud is going to launch by the end of 2025. So you can join our specialist in Hall A1. And with that, I think we can now say thank you. If you have questions, we're here, or reach out to us on LinkedIn. And thank you very much.
Thank you. Bye-bye.